starting from deformation. The concept of deformation is very simple. Deformation means like change in state, shape, size, volume, etc. Whatever we want to write. So this concept is called deformation, and definitely this change takes place because of the application of force on the body. When we exert force on the body, so then we will get this type of change in the body, like change in shape, size, volume, etc. And there are multiple type of changes that can occur in the body. For example, if we consider football, so when we kick football, so football is like in sphere shape. So definitely the change in the shape of the football will be different. If we stretch or compress the spring, so spring is like different shape from the football. So there will be a different type of change in the spring as compared to the football. So basically, in this way, different bodies have different types of deformation. But right now in our syllabus, we are only going to discuss about the change in length. So change in length wise is the main concept in our chapter that we discuss. But there are other types of differences also available. But right now we only focus upon stretch or compress like in single length. So that the type of deformation we will discuss. So whatever the type of change we want to show, that can be shown with the help of deformation. And definitely we are only asking about stretching or compression in the body. Stretch or compress. So this is our main theme of the chapter. We will only focus on stretch and compress on the body. And from the previous syllabus, we know that there is like a Hooke's law in which we are going to use load and extension. So we have one term related to extension. So in extension, we call it like change in length due to the application of the force and it can be defined in very simple way. For example, extension can be represented by symbol X. Final length minus initial length is equals to extension. And this extension like could be positive or negative because we are talking about stretching or compression process. So when we are going to stretch, so length increases. But let's suppose if we compress the spring, so definitely length decreases as compared to the original length. So when length decreases, so definitely the new length will be less than the previous. And when we stretch the spring, so definitely length increases as compared to the previous length. So there are two types of extension we can use, like either positive. So we got positive answer when we increase the length, and we will get negative answer when we decrease the length. So this is the concept of extension. Then after this we have Hooke's law. In Hooke's law, we can say within the limit of proportionality, within the limit of proportionality, the force applied is directly proportional. The force applied is directly proportional to the extension. Basically, in a previous course, we used to write elastic limit or limit of proportionality. So we consider both terms like are same, like both gives you the same idea. Either we write elastic limit or limit of proportionality, but these two terms are not exactly same. There is a difference between them. But in previous course, we are learning the basics. So that's why we consider them like both terms are same. Both gives you the same idea. But right now, in A levels, we know that both terms are not same. That's why we are using different terms, elastic limit and limit of proportionality. So both makes different sense. So now in A levels, we will compare their differences also, like how they are different from how they are different from each other and how to differentiate between them in graphical representation or in any specific case. So first of all, if we write down the formula F equals to Kx, and the value of K represents spring constant, and spring constant means the value of K actually shows the stiffness of the spring or stiffness of the body, because it depends upon the body. Whatever the body we are using, it is not compulsory that we always use a spring. We can stretch or compress any other like tin cane, if we consider the shape of the tin cane, so we can compress that body. So it depends upon the stiffness. So for example, this value of K represents stiffness of the spring, because we are talking about the spring example only. So it tells you about the stiffness of the spring, and stiffness of the spring in simple words, it means that how difficult is to stretch or compress the spring. So it means how difficult it is to stretch or compress the spring. So this is the meaning of stiffness. And for example, if the value of K decreases, let's suppose if the value of K decreases, it means that the spring acts like a soft spring. For example, if we consider the ball point or the ball pen that we used to write, so there is also like a spring in the ball pen. So basically, that spring is very soft. It means for that particular spring, the value of K is very small, because that is very soft spring. We can easily change the shape of the spring or the size of the spring permanently. Okay, so basically, We were talking about the value of K. So basically value of K represents the stiffness of the spring, like how easy or how difficult it is to compress or stretch the spring. And we discussed the example of the ball pen. Like in the ball pen, there is a spring also, and that spring is very soft as compared to any other spring. So if we consider spring in the machines or if we consider spring of the ball pen, so definitely there is a large difference between them. So basically, when we use a soft spring, so in soft spring, what happens? You can easily compress or you can easily stretch that spring. In the same way, if we consider the spring of the ball pen, so if you apply a little more force on it, so it permanently changes shape. So it means the value of K is very, very small for that spring of ball pen. But let's suppose if we consider the springs in the suspension of the car. So in the suspension of the car, we use very strong spring. Like if we need to apply very large amount of force to permanently change their shape, right? Because it is not very easy, just like the spring we used in the ball pen. So it means that if the value of K decreases, it means it acts like a soft spring. And if value of K increases, so it works like a hard spring, difficult to stretch or compress. So this is the general difference between the value of K, like how to differentiate with the reference of value of K. Now the second important part that we discuss, that why the limit of proportionality and the elastic limit, these two terms are different from each other, and what is the difference between them, how we can differentiate them, because in previous course we study both terms are like the same terms, there is no difference between them. So for that, let's suppose if we consider graphical representation. So basically, in graphical representation, we have a straight line first, and then we got a curved line. And for example, on x-axis, we are using extension. On y-axis, we are using load or force. So in this graphical representation, we know that we got a certain time, a straight line. So this is one point. And after this point, we got a curved line. So for example, starting from origin, if we consider O origin, this point A, this point B. And first of all, if we explain the graphical representation from O till A, spring constant is same. So F is directly proportional to X, and F equals to Kx is a valid equation. And let's suppose if we consider a situation from A to B, so now we observe from A to B, it is not directly proportional anymore. So curve shows the value of K changes. So F is no longer proportional to X. So this is the scenario that we observe from the graph, and from this scenario we can also differentiate limit of proportionality and elastic limit. So basically, if we compare limit of proportionality, limit of proportionality, so in short we are writing LOP, limit of proportionality. So what happens in limit of proportionality, and when uh, can we use this term limit of proportionality? So it is the point in graphical representation or like in practical experiment also, where f is directly proportional to x and we got a straight line. So until we got a straight line, just like in the graph from O to A, we are getting straight line. So this straight line shows that point A is limit of proportionality. So the point until we got a straight line, so that point is called limit of proportionality. So limit of proportionality means the point till which f is directly proportional to x and the fx is a straight line. Number two, elastic limit. EL, elastic limit. So basically, if we consider elastic limit, so elastic limit is a point that if you reach beyond that point, so permanent deformation occurs in the body. Just like the example of the spring we were talking, if you apply a little more force on the soft spring or spring of the ball pen, so the shape of that spring will permanently change. So it means you exert force beyond the elastic limit, beyond the limit of proportionality, even beyond the elastic limit. So basically we cross two different limits. So both are not same. So it is the point beyond which permanent deformation occurs. So this is the difference between elastic limit and limit of proportionality. Okay, you shared a question and you mentioned which graph represents the force extension relation of a rubber band that is stretched almost to its breaking point. And you asked that how this is A. Okay. Almost to its breaking point. So force is increasing. Basically, when you reach the breaking point, right? For example, if you consider a straight wire, we have a straight metal wire and we make loops from that metal wire, right? So it becomes a spring. So when you again try to stretch that spring, so definitely it reach its maximum length, right? For example, if there is 1 meter length given of a wire, for example, and when we make a loop from this wire, so it will be something like this, right? This is initial condition. This is final condition of the wire. So definitely when you stretch this spring, so it can maximum extend to 1 meter, right? Because 1 meter is the length of the wire originally. It cannot extend further than 1 meter. It will extend like 1.001 something that value, but not like a very prominent change. So in the graphical representation that you share, in that graphical representation you can observe that extension is now it stopped increasing, only the force is increasing. The reason is the same. When we take 1 meter length of the wire, so definitely 1 meter is the maximum length that we can extend. If we try to extend more than 1 meter, so definitely wire it starts to break into two pieces, right? So that's why option A is correct. Because if you consider option B that is given in the graph, so you observe that extension is still increasing. So it means in option B, the spring will not reach its breaking point. It is still expanding, right? So when you expand till the last point of the body, just like elastic limit, so if you cross that elastic limit, so then we will move towards the breaking point. Just like rubber band, when you stretch the rubber band, so it starts to become thin as compared to the initial condition. If you consider a thick rubber band and when you stretch it, so it starts to become a thin rubber band. And after that, it starts to reach that breaking point. And in option D, it is like in its start, we follow Hooke's law, like force and extension both are directly proportional. And after that, graph D represents force becomes constant and extension is automatically increasing on that force. For example, if you increase the force 1 Newton, 2 Newton, 3 Newton, 4, and let's suppose after reaching the 5 Newton force. So after reaching 5 Newton force, extension is automatically increasing because force is not increasing, extension is automatically increasing in option D. So that's why D is also not a good choice because at a certain value of force it shows extension increases continuously. Okay. Okay. So this is the difference. So after this concept of elastic limit and limit of proportionality, now we consider one more graphical representation because they also used to ask about that graphical representation in exam. So let's suppose in this graphical representation, we have force given, we have extension given, and we consider the same graphical representation. First is straight line and then a curve. So now basically in this graphical representation, until we got a straight line, so there is limit of proportionality. And then we got elastic limit. And after elastic limit, permanent deformation is going to occur in the body. So if we draw a projection from elastic limit to the first region, or the region on the left hand side, is called elastic region. And this is called plastic region. Because in plastic bodies, what happens, if we try to stretch or compress the plastic body, so it will permanently change their shape, right? It will not work like the spring, that it starts to extend or it starts to compress and then it starts to change the shape permanently. In if you consider any plastic body, if you try to twist that body or compress that body, so definitely we observe a permanent type of change in that body. So that's why after elastic limit, we called it a plastic region, right? So this is the difference between elastic limit and uh, limit of proportionality, and this is the region that shows you the elastic region and plastic region. Okay, after this concept, now if we further move towards the idea of loading and unloading, because if we are performing the Hooke's law experiment and we are adding up mass continuously, like 10 gram, then more 10 gram, 20, 30, 40, 50, 60, 70, etc. So after increasing mass like this, we can also unload the mass. Like we reach value 80 grams, then we again it starts to decrease by a factor of 10, 70, 60, 50, 40, 30, 20, 10. So it will give you two readings in two columns, and it will be easy for us to take the average, right? So that's why we used to perform experiment with the idea of loading and unloading, because it will give you an average value to get accurate results. So for example, if we consider first type of graphical representation within the limit of proportionality, within the limit of proportionality means directly proportional link. So this is a directly proportional line, and this is the directly proportional line between force and extension meter. So this is the first type of graphical representation. So for example, if we consider this graphical representation, so first, when we are loading the spring, so definitely graph moves in upward direction. So this is the part of loading. And then when we starts to unload the spring, right? When we decrease the mass again one by one, so it moves in the backward direction. So it only happens in uh, the limit of proportionality idea. Like when we are in limit of proportionality, so loading and unloading curve remains the same. Like loading and unloading graph always remains the same, just like a straight line. So on that straight line, extension increases with respect to the force, and on the same line, extension decreases with respect to the decrease in the force. So we will get a straight line. So we can say if force is applied, the limit of proportionality, object returns to original length. And if we consider one more graphical representation, and in that graphical representation, if we uh, load the spring till the limit of proportionality, so let's see what will be the graphical representation then. So for example, in this graphical representation, we have load on y-axis, extension on x-axis. And in this graphical representation, we actually take the body to limit of proportionality. So if we increase the load until the spring reaches the limit of proportionality, so still we will get the same loading and unloading graph, right? So there will be no difference in loading and unloading graph. The first part actually represents the loading part. This one is loading, and the downward line shows unloading. So this is the concept of loading and unloading. So basically, if we reach the limit of proportionality line, so it still returns to the original position, because elastic limit is not crossed. And one more graphical representation in which we cross the elastic limit, or if we reach the elastic limit point in the spring. So let's see what happens then. Like this. So in this graphical representation, we will get one more line like this. And this line shows when you start loading up the spring. So we follow this path. But after unloading, it will not reach its original value, because originally we started from 0. But after unloading, we observe that our value is greater than original value. It means we cross the elastic limit. And when elastic limit cross, so just like we discussed, permanent deformation occurs. So because of permanent deformation, the shape of the body or the shape of the spring permanently changes, and length also changes. So in this graphical representation, this is, let's suppose, limit of proportionality. This is elastic limit, and this is a permanent extension. XP means permanent extension. So we can also mention over here, if we apply force beyond elastic limit, permanent deformation occurs, right? So this is the different idea. And now you can easily differentiate that why we are using limit of proportionality and elastic limit as a different terms, because in both concepts we got different idea and different representation of the graph also. And the third graph also shows you the change in the length, the change in the original length of the spring, and finally we are not getting that original length back, we are getting some different length this time. So this is the concept of the permanent deformation. And in this permanent deformation, if we talk about elastic potential energy, for example, if we want to find out the elastic potential energy from the spring, so in graphical representation, we have two choices. Either we can find out the gradient of the graph, or the next option, other option is that we can use the area under the curve, and that area under the curve will also gives you another quantity. So from these two concepts, let's suppose if we consider the same graph f with x. So let's suppose if we find out the gradient of the graph, so that is equals to the value of k. So the gradient of the graph always shows you the value of k, gradient of is equals to spring constant. And secondly, if we talk about the area under the curve, so area under the curve shows you elastic potential energy. So if we consider a simple graphical representation like within the limit of proportionality, so just like in the second graph or in the first graph, we are getting a right angle triangle. So in right angle triangle, if we apply the formula of area under the curve, so area under the curve will be equals to 1 over 2 base into height. So base is equals to x, height is equals to f. But we are going to consider an average force. So this is a slight difference. So for example, if we consider elastic potential energy idea, elastic potential energy. So according to the idea of elastic potential energy, we can derive elastic potential energy in this way. It is equals to the work done also. But we consider the average force, like initially it is 0. Finally, it is maximum divided by 2 multiplied by S. That is equals to extension. So elastic potential energy will be equals to 1 over 2 Fx. So, from this idea, we can observe the graphical representation. So, if there is like a right angle triangle in graphical representation, so from that right angle triangle, we can easily find out the area under the curve. And that area under the curve will be equals to the elastic potential energy of the body, right? So if they ask about elastic potential energy, so definitely elastic potential energy can be derived from area under the curve, or in any graphical representation, we can use area under the curve to find out the elastic potential energy. And if we consider the third graphical representation, this one, where we got permanent deformation. In other two graphs, we know that it returns to its original position. So when they return to its original position, so definitely we got elastic potential energy. And in the third graphical representation, it not like reach the original value again. So then how to like explain the complete idea of the transformation of the energy? So basically, in this representation of the graph, because the initial loading line shows you a right angle triangle, but the next line moving in downward direction, so we got some gap between both lines, and the gap between both lines shows some area covered in that specific region. So basically, this type of energy is called, this is the elastic potential energy stored due to permanent deformation. So this is the elastic potential energy that is stored due to permanent deformation. Permanent deformation means it this type of energy, or this elastic potential energy, is the amount of energy that lost in the form of heat. So it is the lost form of energy. Lost in form of heat. So basically this region shows the amount of energy is actually lost, and this is not useful amount of energy. So this is another idea related to the concept of energy. And from the formula of elastic potential energy, let's suppose on the place of F, if we use Hooke's law, so it will be equals to kx. So in this formula, half Fx, so F can be replaced by the value kx, so elastic potential energy will be equals to 1 over 2 kx into x, kx square, right? So this is another formula of elastic potential energy. For example, if the value of force and extension is not given, so we can use the value of k and x with the square of x, and that will help you to find out the value of elastic potential energy from the graphical representation of the spring. Basically, it depends upon the scenario. Like if you in graphical representation, or if the value is given in the question, so if you observe that f and x both values are given, so we can use direct elastic potential energy formula. And for example, if f value is not given, the value of k is given, so we can use half k x square value to find out elastic potential energy, right? In MCQs, when we will practice after completing the chapter, so then you will find in MCQs mostly that we use both type of equations in MCQs, right? So this is the concept of the spring.